let's talk about composite extensions. Now, definition, suppose I have two subfields of C, so I'll only worry about subfields of C, but of course all these definitions are more general. Given two subfields, their composite field is the field which is usually denoted K1, K2, and it's just the smallest subfield of C which contains their union, so it contains both of them. The smallest subfield of C containing both K1 and K2. Okay. Another way of saying this is to say you just take the intersection of F, where I'll put script F. So what is F? F is a subfield which contains K1 union K2. F is a subfield of C. Okay, so this is called the composite of two given subfields of a larger field in general. Now, the most important example of this, which it is really the way in which it will arise, is if I give you a polynomial with rational coefficients and suppose K is the splitting field of this polynomial. Okay, so it's the splitting field inside the complex numbers. So I have Q and I have K, which is the splitting field of Q. Now suppose I just pick some arbitrary subfield of C. So all these are subfields of C. Okay, so now let L be just any subfield. Okay, then the composite. So what does it mean to say K is the splitting field of Fx? It just means that this is obtained from Q by adjoining the roots of F, right? So alpha I in the complex numbers are the roots of this polynomial F. So you adjoin them to Q, you get this subfield K. Now if you take an arbitrary subfield L, so the key word here is it's a splitting field over Q. Now the composite KL is, well, what is it? It's the smallest field which contains both K and L, right? So now observe, just by definition, this is the smallest subfield of C containing, well, what does it contain? It contains L as well as K, but K is nothing but Q and the n roots. So if you just take the smallest subfield which contains all these three sets, L, Q and the set of roots, then that's exactly KL, just by definition. Okay. So of course any field contains Q necessarily. So observe, this is nothing but it's the smallest subfield of C which contains L and the n roots of this polynomial. Okay, so here's the final conclusion. KL is nothing but L adjoined alpha 1, alpha 2, alpha n. In other words, therefore, this is exactly what you would call, this is the splitting field of this polynomial Fx, okay, but thought of as a polynomial with coefficients in Lx. Okay, when I say it's a splitting field of Fx over L, i.e. what I mean is you just view this polynomial as, since it has rational coefficients, you can think of it as having coefficients in L, because L is bigger than Q. Okay, and the splitting field over L is really L adjoined the n roots. Okay, and so that's exactly the composite. So all this is just definition, more or less. Okay, now here's the key theorem which allows us to work with composites. Okay, so it says, suppose I have subfields of C. Okay, such that F is contained in both of them. Okay, now if one of them is finite and Galois, so let's start drawing a picture maybe. So just go to the next page. So I have F Now F is contained in K, it's also contained in L. So in fact F is contained in their intersection, right? So I have this field K intersection L, and F is contained in their intersection. So let me just draw these lines. Of course everything is contained in C, okay, so I'm not drawing C here. Now the field KL that we are talking about, which is the composite, that certainly contains both K and L by definition, right? So it's bigger than both K and L. And as I said, everything is inside C. So this is the picture now, okay? So this is what's given. Now given fields F subset of K and L, suppose I have the following assumptions. If K over F is a finite Galois extension, then so is KL over L. Okay, so this is the first part of the theorem. It says, suppose K over F is a finite Galois extension. So what is that? K thought of as an extension of F is Galois, then KL over L is also Galois. Okay, so I'll just indicate anything that's Galois by this. Maybe we'll just put it in green. So when I put something in green, that's the Galois extension. So here's the Galois extension. You are given that K over F is Galois. Okay, so that's the first part of the theorem. If K over F is finite Galois, then KL over L is finite Galois. Further, you can also say something about the Galois group itself. How are the two Galois groups related? Okay, so the group of KL over L, well, it's not the same as the other group. It's in fact only a subgroup. Okay, and what subgroup is it? Well, you can actually identify it. It is the subgroup K over K intersection L. Okay, so this, recall, is always a subgroup of the Galois group of K over F. Okay, so what are we saying? We are saying the Galois group of this extension KL over L is the same as the Galois group of the extension K over K intersection L. So recall that if K over F is Galois, then K over any intermediate field between K and F is also Galois. Okay, Galois just means normal and separable, and those properties continue to hold when you think of K as an extension of anything between K and F. Okay, so all these are Galois in fact. Okay, so now finally what this theorem says is, let's erase this green guy. So it's like saying these two opposite sides of the parallelogram are the same in some way. It says that the Galois group of KL over L is the same as the Galois group of K over K intersection L. Okay, so that's the content of the theorem. Okay, so let's prove this. So first let's try and see if we can define a map. Okay, so we know that, so first let's check that KL over L is Galois, so that's easy. So remember, K over F is finite Galois, means of course it's a normal extension, so it's a splitting field of a collection of polynomials in general. But if it's a finite extension, then you cannot have an infinite collection of polynomials. It's got to be only finitely many polynomials, of which this is the splitting field, and you can multiply those polynomials together, okay, to get a single polynomial of which this is the splitting field. Okay, so in other words, K, because it's a finite Galois extension, this is the splitting field of some polynomial fx with coefficients in capital F of x. Okay, this is just from normality and finiteness. Okay, since K is normal over F and finite over F. Okay, and now we just now saw that what is KL? KL is just nothing but the splitting field of the same polynomial but over the field L. Okay, so if you think of fx as an element of Lx, then KL is the splitting field of F over L. Okay, which means again by the same token, KL over L is normal, and of course everything here is a subfield of C, so its characteristic 0, therefore it is Galois. Okay, good. Now that's all right. Now we just need to establish that the Galois groups of these two things are the same. Okay, the two green sides have the same Galois group. So let's try and define a map now between, from the top Galois group, which is KL over L, to the Galois group of K over F. Okay, K over F, not K over K intersection F. I'm just going to define a map to K over F. Okay, so the map itself is obvious. So what is this map? This is just take any element sigma in the Galois group of KL over L. That means that what is sigma? It's an automorphism of the field KL, right? So sigma, therefore recall, is nothing but a map from KL to KL from the field on top, such that sigma restricts to identity on L. Okay, such that when you restrict sigma to L, you should get the identity map. This is what an element of the Galois group is. So in particular, sigma is a map from KL to KL, right? So let's go back up here. So this is really your picture. So let's take KL here. Let's make another copy of this diagram. So this is KL to KL. And what is sigma? Sigma is just a map from KL to itself, such that when you restrict sigma to L, it's just the identity map. Okay, so on L it is the identity. So I'll just put a dot there to say it is the identity map. Now, how do I get a map? What do I need? I need a map from this to the set of automorphisms of K over F. Well, how do I get a map? I just restrict it to K. So just take sigma and you restrict sigma to K. Okay, so if you go here, sigma is defined on the big set. So all I do is I restrict sigma and to K. I just think of it as a function on K. Now the point is, if I restrict sigma to K, the key observation is that the image will again be in K. Okay, the restriction of sigma to K will map K to itself. Okay, so there are lots of nice parallelograms in this figure. So why is this? Observe, for this to be well defined, if I restrict sigma to K, the claim is that, well, sigma maps K to itself. Okay, proof, well, if you go back and look at the various things we proved about normal extensions and so on, recall that K is a normal extension of F. Okay, now I can think of sigma as a map from KL to L. So if it's identity on KL to KL, if it's identity on L, in particular it's identity on F, because F is even smaller than L, right? So I just think of sigma as a map from KL to KL, which is identity on F, right? So let's erase the thing in the middle. It's just a map like this, which is identity on F. Okay. Now the normality of K. Now the point is K is a normal extension. So K sits in the middle, and K over F is normal. Then one of the equivalent conditions we proved about normal extension is that if you have sort of a map of the algebraic closures, then that map restricts to a map of K. Okay, and here KL is bigger than K. You can always extend this to some larger algebraic closure. So recall by the theorem on algebraic closures, if P is an algebraic closure of KL, any map sigma from KL to KL can always be extended to some map from P to P. Okay, and I mean, we have used these arguments before. So the restriction of sigma tilde to K will map K to itself definitely. Okay, therefore sigma maps K to K by the property of normal extensions. Okay, good. So that at least it allows us to define a map, and it's easy to see that this map is a group homomorphism because we have done nothing. We have just restricted. You're given a map on a larger field, you just restrict it to a smaller field, and so compositions of maps go to compositions of maps. So it's a group homomorphism. So define the group homomorphism like this. So for well-definedness, we need to check this claim, and this claim comes from the normality of K over F. Okay, let's see, where are we? Now what do we need to do? We need to prove two things. We need to first show that this map is a one-to-one map, and secondly, its image is exactly the subgroup that we claimed in the theorem. So we need to prove two claims. So let's prove claim 1, that this restriction map is injective. Okay, first claim. Second claim, its image, okay, let's call its image as something H. It's a certain subgroup of the automorphism group. Its image H is exactly the set of automorphisms of K which are identity on K intersection L. So this is the second claim that we need to make. If we prove these two claims, then the theorem is proved. Okay, now let's, so H, by the way, is just a name that I'm giving to the image here. Okay, it's nothing, it's not a new subgroup here. I'm calling the image as H. Okay, let's prove it's injective first. So what was the map? It takes any element sigma of from aught KL. So let's copy the map. This is the map here. Okay, so here's our map. Okay, now why is this injective? To show injectivity, if sigma restricted to K is the identity on K, then we need to show sigma itself is the identity. Okay, now what does that mean? Well, on K it's already identity. Observe, sigma on L is definitely the identity, because sigma came from this subgroup, right? It was L, identity on L already, which implies that sigma is necessarily the identity on K union L. Right? It's identity on both of them. But what is KL? KL is just the smallest subfield of C which is generated by the union, right, of K and L. So if sigma is identity on the union, then it sort of follows easily that sigma is identity on KL. Since K union L generates KL. Okay, so that's all you need to show injectivity. So the first claim is done. Okay, if sigma K is identity, then sigma KL itself is identity. Now the second claim is slightly trickier. So let's try and prove that. The claim is that the image H is exactly this subgroup. Okay, so let's go look at that diagram again. So we need to show that the image is the subgroup of automorphisms of K which are identity on K intersection L. Okay. Now here we will use the fundamental theorem of Galois theory. Okay. So to prove the second claim, how do you show that two subgroups are the same? Right? They are both subgroups of the group of automorphisms of K over F. So to show two subgroups are the same, it's enough to show that their fixed fields are the same. Okay. So to prove claim 2, by the fundamental theorem of Galois theory, it is equivalent to proving the following assertion, that the fixed field of H is the same as the fixed field of the other group, okay, which was K intersection L in this case. Okay, so we need to say that these two things are exactly the same. Okay, now how does one show that KH is K intersection L? So well, let's at least see, there is a one-way containment. So this is what we will now try and prove. Okay, first observe that elements of H, so if sigma belongs to H, okay, what does that mean? I.e., so we shouldn't call it sigma. If tau belongs to H, what does that mean? That means tau is of the form, the restriction of sigma for some element coming from the Galois group of KL over L. Okay, so what does this mean? Well, tau is sigma restricted to K. Now sigma here fixes all elements of L. Okay, so sigma fixes L pointwise. So the restriction of sigma to K will fix K intersection L pointwise. So this means that tau on K intersection L is just the identity map. Okay, and why is this? Because sigma was the identity, sigma on L was the identity map. Okay, so what does that mean? This means that tau fixes K intersection L pointwise. Therefore, the fixed field, so tau fixes okay. So what does this mean? At least one-way containment we have shown that every element of H fixes K intersection L. Okay, so the fixed field KH certainly contains K intersection L. So that's what we have proved. So let's say that this means that the fixed field of H, just the elements which are fixed by every element of H, this certainly contains K intersection L. Okay, now we need to prove the converse. Okay, now the converse is the slightly tricky calculation. So let's do the following for the converse. Let's do something slightly non-obvious. So let's look at KH. So it's some subfield, right? So what is KH? It is some subfield of K. So therefore KHL is some subfield of KL. Okay, since KH is some subfield of K. Okay, now let's do the following. Let's take all elements of the big Galois group. Okay, now all elements, what do? Well, sigma fixes L pointwise. Okay, in other words, sigma on L is of course the identity on L. This we know by definition, but we also know something that if you take sigma restricted to KH, then what is this? KH, remember, is a sub of K. Right? So how do I restrict sigma to KH? I can do the following. I will first restrict it to K. Okay, K is still bigger than KH, and think of that as being further restricted down to this subfield KH. Okay. Now what do we know? Sigma restricted to K is exactly the elements. Those are the elements in the image, right? So this is like a tau. So this fellow here belongs to my subgroup H, because that's the image of a sigma. And of course elements of H, how do they act on KH? By definition, this is the fixed field of H. Therefore elements from H will necessarily act as identity on their fixed fields. Okay, so this is the slightly tricky argument that one has to work through to understand, but the basic idea is that sigma restricted to KH is like some element of H acting on KH. So that's the identity. Now the same argument that we used before, if an element acts as identity on both L and KH on two fields, then it acts as identity on their union and therefore as identity on their composite. Okay, so same argument as before. So what does this mean? This says that every element here in KL over L, it also fixes KHL. Okay, so this means that KHL is pointwise fixed by every element of the Galois group KL over L. Okay, but then what does this mean? What does the fundamental theorem of Galois theory tell us? It says that if I have the Galois group, so this means that KHL, this field is contained in the fixed field of the entire Galois group, right? So if you call this group G the full Galois group, then this is contained in the fixed field of the Galois group of KL. But the fixed field of the Galois group is always just the field, the base field L, right, by fundamental theorem of Galois theory. Okay, and we are also using, since KL over L is a Galois extension, Okay, so we are using the fact that KL over L is Galois, and therefore the fixed field of the full Galois group has to be the base field. Okay, so what does that mean? It says KHL is a subset of L. Okay, that's a strange thing because L is already there. What it says is if you take the composite of L with this other field, you don't get anything more than L, you just get L itself. That means that KH, in particular this means KH union L is contained in L. This means that KH itself is contained in L. Okay, so what does that mean? KH is contained in L. Also, KH by definition is contained in K. Therefore, together it gives us what we want. It says that KH is therefore contained in K intersection L. Okay, so we have shown the other way inclusion. Therefore, we have shown both inclusions. KH contains and is contained in K intersection L. Therefore, KH is equal to K intersection L. Okay, so it's a somewhat tricky proof, but well, we have managed to do it. So what this means is that the composite extensions, so let's go back and see what the theorem said. If I have, if F is a subfield, let's get rid of this now. So if I have okay, so here's the statement. If K over F is Galois, right, then, so if this whole thing is Galois, then so is this, so is KL over L. Further, the Galois group of KL over L is the same as the Galois group of K over K intersection L. Okay, now let's just finish this up with a little corollary, which is going to be very useful to us. It says the following. Corollary, let FKL be subfields of C, and suppose both are normal, both K, well, I mean, I also want F to be contained in both of them. Suppose KF and LF are both Galois extensions. Okay, finite Galois extensions are both finite Galois extensions with the following property, that the Galois group, so the group of K over F, is non-abelian and simple. Okay, so recall, a simple group means the only normal subgroups of that group are the identity group and the full group. Okay, and B, the other guy is abelian. Okay, one of them is non-abelian simple, the other is abelian. Okay, so they are somehow very different, widely different behavior. Then the conclusion is that K and L cannot really have any intersection other than F. Okay, so I have assumed to begin with that F is contained in both K and L. Okay, with, maybe I should say F is inside both K and L. But what we are concluding is that K intersection L has to equal exactly F. And statement 2, that the automorphism group of KL over L is isomorphic to the automorphism group of K over F. Okay, so again, to draw that picture, it says I have KL, I have K, L, F, but the assumptions here are that both are Galois. K intersection F is a Galois extension, L over F is a Galois extension, but they sort of have these somewhat different behavior. The Galois group is non-abelian simple, whereas the other side it's abelian. This Galois group is abelian. Okay, so if you have this behavior, then the theorem says that K intersection L cannot be anything other than F itself. Okay, And the second part of the theorem, observe, is a corollary to the first one. So this follows from 1 by our previous theorem. This follows from 1 by our previous theorem. Because the previous theorem said that the automorphism group of KL over L is exactly the automorphism group of K over K intersection L. Okay, good. So we just need to somehow establish this. Okay. So it's enough to prove 1. Okay, so that's the first observation. It's enough to prove the first part of the theorem. Okay, so let's prove it. Now, let's maybe give these Galois groups a name. So L over F we know it's Galois with let's say the Galois group, let's give it a name G. Okay, now G is an abelian group, right? G is what's given to be abelian. And let's look at the subfield K intersection L. Okay, it's an intermediate field, and therefore that subfield will correspond to some subgroup. Okay, so let H subgroup of G be correspond. So the fundamental theorem of Galois theory, there is some one-to-one correspondence. So this subfield K intersection L corresponds to a subgroup H, and we know what H is. It's actually the group of automorphisms of L which are identity on K intersection L. Okay, now the key point here is that G is an abelian group and H is a subgroup, therefore H is automatically normal. Okay, H is normal. H is a normal subgroup of G since G is abelian. And the fundamental theorem of Galois theory had something to say about this. If you have a normal subgroup, then it says that the extension here is also Galois. Okay, so again, let's use the fundamental theorem. It says that K intersection L over F is a Galois extension. Okay, now in fact we know the Galois group, it's isomorphic to G mod H and so on. But let's just for the moment do the same thing from the other side. Okay, so let's look at the other fellow, which was K over F is Galois. So let's consider that leg of the diagram, K intersection L F. Okay, now by the fundamental theorem of Galois theory, so what do I know here? I have concluded by using this other side that this is Galois. Okay, I already know that this whole thing is Galois. Okay, now by the fundamental theorem again. Okay, so on this side, so sorry, I should do the same thing on this side. So let me call this group as G prime, the group of K over F, and let's call the group corresponding to H prime as corresponding to K intersection L as H prime. Okay, be the group subgroup corresponding to K intersection. Now again, fundamental theorem of Galois theory says that since K intersection L over F is known to be Galois by other means, this automatically means that this subgroup has to be a normal subgroup. Right? That was an if and only if statement. This has to be a normal subgroup of G prime. Now that's a problem because we have assumed to begin with that G prime is a non-abelian, well, non-abelian is not the key, it's simple, right? Which means that it's got no subgroups other than, no normal subgroups other than the identity and the whole subgroup. So this means there are only two possibilities, which implies either H prime is the identity or H prime is the whole. Okay, now what do these two things mean? If H prime is the whole, then the corresponding field that it corresponds to has to be the base field, right? That's the correspondence. And on the other hand, if it's the identity, then the field K intersection L has to be the big field, okay, which in this case is K. So there are only these two possibilities. But observe, K intersection L is K will mean that K is a sub of L. Okay, so K is actually a sub extension of L. Now, what does this mean? This means that the diagram that we drew actually looks like this. That is F, K comes somewhere in the middle, and then L comes somewhere further up, right? But then observe, L over F was given to be Galois. This is Galois. Okay, and with abelian Galois group. So again, by the same argument that we gave before, K intersection F, K intersection L is K. This is also a Galois extension, and the Galois group, if you remember, Galois group of K over F would have to be, it's a quotient, right? So this would be, in our earlier notation, this is the quotient G mod H. Okay, but whatever it is, G is abelian, so G mod H is abelian. Okay, but we are also given that the automorphism group of K over F is non-abelian. So we've used both hypotheses, is that it is non-abelian as well as simple. Okay, so what does that mean? So that's a contradiction. So this case can't arise. Tells you that K can't be a sub of L. Therefore, the only option is this one, which is K intersection F is K intersection L is F itself. Okay, now there are various modifications of this which will be relevant and that we'll look at in the next video.